Okay, note number 1, any vector v with magnitude of v, and angle theta can be written in component form. So here's what we're saying with a graph. I'll graph v in the first quadrant, although you don't have to. So there's my vector v, and you're not told what the components are. You're told the direction angle is theta, and you're told that the magnitude, the vector, what does magnitude mean? The length. So you're told that the magnitude is, well, generically, just using the symbolism for magnitude, it's the double bars around v. So what we're saying, what I'm about to present to you is a way, given the magnitude of v and the direction angle theta, I'm giving you a way to find the horizontal component and the vertical component. And it just turns out to be that delta x is equal to, so again, I've been using a for the horizontal component, but I've been switching back to delta x periodically to remind you of what that really means. And delta x, it turns out, can be written as the magnitude of v times the cosine of theta. Seems kind of random, but I'll prove that to you in a second. Delta y, it turns out, so delta y is the vertical component, is magnitude v sine theta. And although this looks strange, it just goes back to SOHCAHTOA. Okay? So we drop the perpendicular from the end of from the tip of the vector v, create the right triangle, and it shouldn't be then a big surprise. Okay, we call this horizontal side delta x, this vertical side delta y, right? We'll do one of these. Just use the ka part of SOHCAHTOA to get me the cosine of theta. What would, in terms of what I've written here, what would the cosine of theta be? Look at this triangle. The cosine of theta would be the ka part of SOHCAHTOA, right? Cosine equals adjacent delta x over hypotenuse, which is magnitude v. Now solve for delta x by multiplying both sides by the magnitude, and you get delta x is the magnitude of v cosine theta. And then you could use the so part of SOHCAHTOA to get delta y. So we're back to trigonometry, which you can see now why we're talking about vectors and trig, because you use a lot of trig to derive some of these formulas. So by the way then, if you wanted to write the vector in component form, you would say vector v has components magnitude v cosine theta, comma magnitude v sine theta. What would it look like in ij form? Magnitude v cosine theta times the vector 1, 0, which is I, plus magnitude v sine theta times j. These both represent the same thing in different forms. So this is note number 2. C is a constant. Turns out that the magnitude of C times V, the magnitude of a constant times V, well, it turns out you can pull the constant out as long as you put absolute values around it in case it's negative. So it's actually not too hard to prove that the magnitude of C times V is the absolute value of C, which is just C if C is positive, times the magnitude of V. And that's actually pretty easy to prove using the magnitude formula, the Pythagorean theorem, in other words, and a little bit of algebra. Now, it turns out that you can create a unit vector. What do you think I mean by a unit vector? It means the magnitude of the vector is 1 unit long. It turns out a unit vector is given by, well, v divided by its magnitude. Okay, but we haven't defined division of vectors. Well, what does it mean when the magnitude of v is a number, right? when you divide by a number, it's the same as multiplying by that number's reciprocal. So that really means 1 over the magnitude of v times v. Quick example. Let's take the vector -3, 5 in component form. No, let's make it even easier. Let's make it -3, 4 in component form. What's the magnitude of v? And it's so common you could even do it without the Pythagorean theorem, without the magnitude formula. It's 5, right? When the components are, well, when the absolute value of the components are 3 and 4, the length of the vector, the magnitude of the vector is going to be 5 every time. Okay, because when you draw the picture, it forms a 3, 4, 5 triangle. So if you want, you could use the formula or just realize you have a 3, 4, 5 triangle, and you get the magnitude of v is 5. So according to that note above, I should be able to scalar multiply v by 1/5, and that the resulting vector should have length 1 unit long. It should have magnitude 1 unit long. So 1/5 times the original vector, -3, 4, is 1 unit in magnitude. Do you believe that? That's what the note says. Would that be easy enough to prove? Yeah, it would, because this vector is equal to, if we actually do the scalar multiplication, what components do we get? -3/5 and 4/5, right? The magnitude of this vector, -3/5, 4/5. How do you take the magnitude of this vector? It's the square root of what? Okay, what's a? So -3 over 5. So square that underneath the radical, square that, and add that to what? Something else squared. 4 over 5. And what do you get when you square those guys? Underneath the radical, you get 9 over 25 plus 16 over 25. And of course, that adds underneath the radical to be 25/5, which is 1, and the square root of 1 is, of course, 1. Okay? So for this particular example, we showed that when you divide v by its magnitude, you get a vector of length 1. And so that's what this formula says. Note number 4. Vectors u and v are parallel. That IFF means if and only if. It's a shorthand way of saying if and only if. Vectors u and v are parallel if and only if u is equal to c times v, where c is a scalar. If you separate the pictures and you have a vector like u, maybe it looks like that, what would 2u look like? It would point in the same direction, but it'd be twice as long, right? And if you draw them separately so that one doesn't lie on the other, I mean, if you put them at the same initial point, if you make them have the same tail, then then 2u lies right on top of u, or vice versa, right? But if you separate them, which you're allowed to do with vectors, they look parallel. They're parallel line segments, aren't they? So the definition should be clear why we call those two vectors parallel. And so 2 is like c in this case. But it works in general too, because even if c is negative, it reverses the direction, but the line segments are still parallel. The arrows are still parallel, right? So we call two vectors parallel if they're scalar multiples of each other.